Hi everyone, hope you had a good weekend. So last time we ended off just looking briefly at the net change theorem. So this was an application of one of the parts of the fundamental theorem of calculus. So we know that the integral from a to b of f of x is equal to the difference in the antiderivatives, right? So you have the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. And we saw that if you replaced f with f prime, or the derivative of f, then we get this formula here on the second line. So the integral of the rate of change of f is equal to f at the end point minus f at the starting point. And we called that the net change in f. So you can think of that as final minus initial gives us the net change. Yeah, and then we did a little example of a kid running with some speed. And we found that if you integrate the speed over the time interval, then you get the distance that is traveled. Yeah, and we came up with this little thing to help us remember the net change theorem. So the sum of small changes gives us the total change. And that's just a little way of remembering this formula. So when we say the sum of small changes, we mean the integral of the derivative, because remember the derivative means changes, is equal to the total change. Well, that's the right-hand side here. Final minus initial, that's the total change. Okay, so we're going to carry on now with a few more applications and examples. Okay, so the first thing is that the net change theorem is very general. So it is very general. In other words, it applies to lots of things where things are changing. So it applies to lots of situations where things are changing. Okay, and just a couple of examples. Like we said before, with speed and velocity, that means your distance is changing. So we can put speed, velocity, and then if your speed or velocity is changing, then we call that acceleration. So again, wherever things are changing, we can use the net change theorem. Okay, another example is population. So let's say you have a population P at some time T. We want, if we can measure how the population is changing, so that is the derivative of the population with respect to time. Let's say this is 3t minus 1, for example. If this is the rate of change of the population, then if we integrate this over a time interval, it will give you the total population. Okay, so that's a typical example. Another one, and you'll see this in the tutorial, is densities. Okay, so this is used by the engineers and the physicists. We say that the density of something, or the mass density of something, we call that rho, and that is the mass divided by, well, if in this case, we're talking about like linear mass density, it's divided by L. So here is the mass, and here is the length of the object. And if we're talking about linear mass density, we're talking about like rods, because those are long. Okay, so what this density says, the mass per unit length, it's saying that at a given point, so at this point here, how much mass is there? How much mass is at this point? Okay, and then you pick another point and you get another mass. In other words, we have this function rho of x, where we go from 0 to the length of the rod. And this can be given by some function. Let's say x squared plus 3x minus 1. So that's the mass density. It's the mass per unit length going along the rod. Okay. Now, what happens if we want to find the total mass? Well, we see that this density is actually a derivative because it's the mass per unit length. So we can actually write this as the change in mass over the length. So dm by dx. That's the density. We call the density rho. Okay. Now, if we want to find the total mass, we need to undo this derivative. And so we use the net change theorem. So in this case, the mass will then be the integral of the density along the rod. So from 0 to L. Okay. And then that gives us the total mass. Okay. Are there any questions about this example with mass density? Okay, so it's just an application. Okay, but the thing that we're going to focus on now, because it's going to come up in your tutorial and the tutorial test, is this first one on speed, velocity, and acceleration. And this, I think this one's also in your tutorial as well. Okay, so let's go through this idea of speed, velocity, and acceleration. So speed and velocity. Okay, so let's just start off with the definition so we're all on the same page. So speed is the magnitude of how fast you are going. Okay. So everyone knows what speed is. You're driving in a car, you see the speedometer. But the key thing is, it is the magnitude of how fast you're going. Okay, so it is always positive. Okay, it's just some positive number that talks about how fast you're going. So speed is always positive. So that's the key idea. Now, if there's any physics students here, you'll know about this one. Velocity is your speed together with the direction. Okay, and then the way that we specify the direction is with a sign. So either positive or negative sign. Okay, so speed is just the magnitude of how fast you're going. It doesn't tell you in which direction you're traveling. It just says how fast. On the other hand, velocity is speed together with your direction. So it has extra information that tells you where you're going. So usually, if you're going to the right, okay, so this is in like one dimension, you can go to the right or to the left. So to the right is positive. And to the left is negative. Okay, now of course there's up, down, forward, back, but we're only going to consider one-dimensional motion for our tests and examples and all of that. Okay, but if you're ever confused with something in the test or anything, just remember here, if the object is going to the right, then the velocity is positive. If the object is going to the left, then the velocity is negative. We're going to stick to that. Okay, so let's look at an example of the differences between speed and velocity. Okay, so I'm just going to draw two graphs here just to illustrate this. So here we have time and here we have speed. Okay, and speed will always be given with S. Okay, so S for speed. So here we can just draw a little graph, something like that. And then we can see at some given points, let's say this point here, at this time, we see that the speed has some certain value and the speed is going up from that point. So it's increasing. So speed is increasing. Okay, because we're going up that little slope there. So the speed is increasing. But you can see from this graph that we are only ever in the positive region. Okay, the speed is never negative. We always write it in a positive way. On the other hand, if we have velocity, okay, so here we have time, here we have velocity. Now, velocity can be negative. And we know if it's negative, it means the object is then going to the left. So here we can draw something maybe like this, like that. Okay, so let's take a look at this first region here in yellow. So everything highlighted in yellow there, that region, we see that that region is positive, which means the object is going to the right. So this is moving right. Then at this point, we see that the velocity is 0. So if the velocity is 0, it means the object is not moving anymore. It's stationary. Then for this next region, this region in green, we see that this region is negative. So this means that the object is moving left. Yeah, so it was moving right, it stopped. So let me just put here, it stopped. And then it started moving left. And then at this point, it stopped again. And now it turned around and now it's moving right again. So this is now moving right. So you see, we have this extra information available. If we're looking at the velocity versus time, we see that we have information about how fast the thing is going, the velocity. But if it is above the time axis, we know that it's moving to the right because it has positive velocity. If it's below the time axis, the velocity is negative, so we know it's moving to the left. If we look at this graph of speed versus time, we don't know where it's going. Okay, it might be moving left or right. We can't tell. Okay, so you see that this velocity versus time has more information. Okay, so just please keep these two graphs in mind while we look at the net change theorem for distance. Okay, so firstly, we're going to look at the idea, first, we're going to look at the differences between distance and displacement. Distance and displacement. Okay, so both of these concepts, distance and displacement, they use the ideas of speed and velocity. So it's important that you understand these differences here. Okay, so distance. So distance is the total length of your path that you took. Okay, so whether you went left for a bit and then right, or maybe you went right for a long time and then you went left, that doesn't matter. It's the total length of the path. Okay, so whichever path you took, you went left, you went right, then you went left again, doesn't matter. The total length of the path that you took, that's the distance. On the other hand, displacement is just your final position minus your initial position. Okay, so for displacement, we're not interested in the path that you took. We're only interested in where did you stop, where did you begin. You take the difference between those two, and we call that your displacement. Okay, are there any questions so far? Okay, so let's look, how do we find this distance and displacement? Okay, so in both cases, we begin with the definition for speed. So remember, speed is the rate of change of distance. So we write that as dx by dt. So x, that is your position, and t, that's of course time. Okay. We could also write this as x prime of t. Okay, so that's your speed. So we see that speed is a derivative. Now, since it's a derivative or it's a rate of change of something, we can undo that by using the net change theorem. Sorry, and this is also given by S of t. Okay, so if we want to undo this derivative, we then need to integrate up the speed to get the distance. So the distance is equal to the integral, let's say from t1 to t2 of your speed. Okay. Because remember, speed is the rate of change of distance. So if we go back to our, here we go. The f prime, that's your rate of change. If you integrate up your rates of change, then you get the net change. So the same thing applies here. We integrate up the speed, you get the change in the position or your distance. Okay, so this is the first thing that we need to remember. Okay, so that one's easy. Just going from speed to distance, no problem there. The problem comes in when we are looking at the velocity. No, sorry. Jumping ahead here, distance equals the integral from t1 to t2, the velocity with respect to time. Okay, now remember the difference between speed and velocity. Speed is always positive. So when you integrate up your speed, you're going to get a nice positive value, which will be your distance. However, velocity can be either positive or negative. So what happens if the particle or the object is always moving to the left? Well, then the velocity is always negative. And if we're integrating up a negative function, we're going to get a negative distance. That doesn't make any sense. So what we need to do is put absolute value over the velocity. Okay, so if we want to find the distance and we're given the velocity, we need the magnitude or the absolute value of velocity. Yeah, because we want to sum up the total length traveled. We're not interested in whether you went left or right. The distance doesn't matter. We still add up for the path that you take. Okay, are there any questions about that? Okay, so if we just go back here, we see that for velocity, there's positive parts and there's negative parts. If we want to find the distance, we need only positive parts. So we take the absolute value, it makes everything positive, And then summing that up, we get the distance. Okay, and then the last thing that we need to know for this is displacement. So remember what I said displacement was, that is your final position minus your initial position. So in that case, we need to use the velocity, because remember the velocity gives us the direction. So which way are we going in? So if we want to know the displacement, we need to integrate from T1 to T2 of just the velocity. Okay, because displacement can be negative. So if you take some, let's just draw it here. Okay, so let's say here's your 0 point. If you moved this way, then turned around and came back, and then went back there, and then you ended up back here. So here is the start. Here is the end. We see that the displacement is this portion over here, and we see that it's negative. Okay, because you ended up on the left-hand side of where you started. So the displacement is negative. So in this case, for displacement, we do care about the sign. So we need to integrate the velocity, but no absolute value. We have to keep the sign, because if we end up on the left-hand side of where we started, we need the displacement to be negative. So the sign is important here. So let's just make a little note here. The sign of velocity is important in this case. Okay, so these are the three things that you need to remember. If I give you the speed and I ask you for the distance, you just integrate the speed and everything's fine. If I give you the velocity and I ask you for the distance, you need to integrate the absolute value of the velocity. Because remember, we want the total length of the path. So we're not interested in the sign of the velocity. So we take the absolute value to make it positive only. And then that gives us the distance. If I ask you for the displacement and I give you the velocity, then you just integrate the velocity. And note that you cannot find the displacement using the speed, because speed is only positive. So you can't work out the displacement using that. Okay, displacement only goes with velocity. Okay, are there any questions about that? Okay, so everyone's okay with this idea of distance, displacement, speed, and velocity? Okay, let's look at an example. Okay, so I'm going to give you the velocity. So let's say the velocity as a function of time is equal to minus t squared plus 2. Okay, let's start off simple. So we have minus t squared plus 2. Now this function here, remember, it can be positive, it can be negative. If it is negative, that means the object is going to the left. If it's positive, that means the object is going to the right. So question 1. What is the displacement over the time interval (0, 3). Okay, so now we want to know displacement, which means we don't care about the path. All we care about is where did you end, where did you begin? You take the difference. So in that case, we just have to integrate up the velocity. We don't have to do absolute values or anything. because the sign is important. So let's just make a little note again. For displacement, the sign is important. So we don't take the absolute value. So in this case, the displacement is equal to the integral from 0 to 3, because that's our time interval. The velocity is minus t squared plus 2 dt. Okay, no absolute values or anything like that. Okay, so now this is going to be, we find the antiderivative and all of that. So remember FTC 1 and 2. So this is going to be minus 1/3 t cubed plus 2t from 0 to 3. So in this case, it will be minus 1/3 3 cubed plus 2 times 3. And then if I substitute 0, I'm just going to get 0. So we don't worry about that. So this is going to be 3 cubed over 3 with the minus. So that's minus 9 plus 6. That's minus 3. And a big emphasis, it is minus 3. It's a negative value, which means the object may have moved to the right some amount, it may have moved to the left, but it ended up 3 units to the left. Yeah, so that's where it ended up. It ended up 3 units to the left after the motion. Okay, but we just leave it as minus 3. Yeah, so again, if we want displacement, the sign is important. And we see clearly in this example, we get a negative answer, which means the final position of the object was minus 3, or 3 units to the left, either way. Okay, but please remember to put in the negative sign. Okay, just by convention, we say negative is to the left, but I'd rather have this explicitly shown as negative. Okay, so please do that. Okay, so please leave as a negative. Okay, so it just emphasizes that the sign is important. Okay, are there any questions about finding the displacement? Okay, good. Let's take a look at the next question, finding the distance. Yeah, so distance, remember, if I give you the velocity and I ask you for the distance, we then have to integrate the absolute value of the velocity. So distance is equal to the integral from 0 to 3, the absolute value of minus t squared plus 2, minus t squared plus 2 dt. Okay, now we can't just integrate an absolute value like this. We need to find out explicitly where is it negative, where is it positive. So let's look at the function and see where is it negative and positive. So for that, we need to find the zeros. So minus t squared plus 2 is equal to 0. We have t plus root 2, t minus root 2 is equal to 0. So we see that at root 2, at t equals root 2, the function is 0. Now, we're not interested in the negative solutions because remember, time is positive. Okay, time goes from 0 up to infinity. So we're not interested in negative times. So here we see that at 0, we go along the t-axis, we have the velocity is 0 at root 2. Can you please re-explain number 1? Sure, I'll get to that now. Let me just finish this part with the absolute value and then we can go back there. Okay, so we've got this here. So that's one of the zeros there. And then There's another one at minus root 2, but we're not interested in that. Okay, and we see that this is a sad face parabola because it's minus t squared. So it's going to be positive here, negative there, negative there. So from 0 to root 2, it's going to be positive. And from root 2 onwards, it's going to be negative. So we see that after root 2, we need to flip the sign because it's a negative there. So this is going to be the integral from 0 to root 2 of minus t squared plus 2 dt. So that's for the first part where it's positive. And then for the second part, we need to flip the sign. So plus the integral from root 2 to 3, we need to put a minus sign now because it was negative. So it's going to be t squared minus 2 dt. Okay, so you see we split it into two parts. The first integral handles when the velocity was positive. The second integral handles when the velocity is negative. In other words, we put the absolute value on. Another way of writing this would be minus t squared plus 2 is equal to minus t squared plus 2 for 0 less than or equal to t less than or equal to root 2, t squared minus 2 for root 2 less than or equal to t less than or equal to 3. Okay, if you want to write it out like that. Okay. So let's do this. So this becomes minus 1/3 t cubed plus 2t from 0 to root 2 plus 1/3 t cubed minus 2t from root 2 up to 3. Okay, so for this first part, we get minus 1/3 root 2 cubed plus 2 root 2. And if I put the 0, I'm just going to get 0, so I'm going to leave that. Plus 1/3 3 cubed, that's going to be 9, minus 6. And then minus, if I substitute root 2, I'm going to get 1/3 root 2 cubed minus 2 root 2. Okay, so I've just substituted everything there. Okay, let's see what we get. So root 2 cubed, that's going to be 2 root 2. Okay, so we can write this as minus 2 root 2 over 3 plus 2 root 2 plus 9 minus 6, so that's going to be plus 3 minus 2 root 2 over 3 and then plus 2 root 2. Okay. So we can write this as 3 and then plus 4 root 2. Okay. And then minus 4 root 2 over 3. And then we can simplify this. So 4 root 2 minus 4 root 2 over 3. We can do a common denominator of 3. So then this becomes 12 root 2 over 3. So that's going to be plus 8 root 2 over 3. And then you can leave it like that. That's fine. Okay, so you see we get a positive answer for the distance, which is what we expected. Because remember, distance is just the length of the path taken. So it always has to be positive. Okay, let me just go over the part 1 again. Someone asked for that. Okay, so for part 1, we are looking at the displacement. So this object is moving according to the given velocity. We want to know the displacement. So recall that the displacement is equal to the integral from t1 to t2 of just the velocity. Okay, no absolute values or anything like that. Okay, so we're just integrating the velocity. So here we integrated the velocity and we get -9 plus 6 after substituting the bounds. And we get an answer of -3, which means if we look at the, like, let's say here is the x-axis where the object is moving. It started somewhere here, let's say. Okay, so that's the start. Okay, wherever it started, doesn't matter. It moved here, then maybe came back, then maybe it went back there, but it ended up here. And this point is x equals -3. So this distance here is on the left from where he started. So the displacement is -3. So this bit here, this is the displacement. And it is equal to -3. So that's what we get after the integral. Okay, so remember, for displacement, it doesn't matter what path you took. We're just interested in the final position minus the initial position, and that gives us the displacement. Okay, does that answer your question? Okay, sure, no problem. Yeah, so it's like this over here. Just go back here. Yep, net change theorem. So we're integrating up the velocity. So that means we're looking at the final position, because the integral of velocity gives us position. So the final position minus the initial position, that gives us the net change in position, which we call displacement. So here we see that the final here was -6. The initial was 6. So the displacement was -3. Okay, so that's where they ended off. Sorry, this is a delta. Sorry, that's a delta x there. Delta x is -3. Okay, so in this case, the start was. Oh, no, that doesn't matter. Okay, so yeah, delta x -3. That's the displacement. So the physics students would be using delta x. You can use that in the test, that's fine. But I do recommend just writing out displacement like I wrote here, or writing out distance. Okay, it just helps with the marking. Okay, but for the physics students that use delta x all the time, you can use that as well. I don't mind. Okay, so that's it for today. There will be another lecture